Welcome to Module 4, Lesson 16, Population Problems. Yes, this Lesson 16 is the first lesson in the final topic, Topic C, Lesson 16, 17, and 18, and that will be the end of Module 4. So in Lessons 16 through 18, we will see some further applications related to percents. Okay, so we've learned quite a bit about percents, and some of what we've been doing in this module has been a throwback to Module 1, and hopefully you are becoming more and more comfortable with working with things such as constant of proportionality, different rates, scale, factors, and all of that, and you will be able to take those on again once you see them next year again. Okay, but yeah, in 16 through 18, kind of an extension of what we've been learning thus far, we will see problems involving populations, mixtures, and counting. Okay, so that'll be lessons 16, 17, and 18. Okay, so let's get right into it. All right, so here we go. We have a population problem. Okay, population problems right here. And the population is going to be our classroom. Okay, and of course we're not there in our classroom. Okay, you are there at home or elsewhere. But I will give you some numbers, and you can do some figuring on your own. Okay, so first numbers are right there. In our class of 14 total students, we have 8 girls and 6 boys. Okay, so why don't I have you go ahead and fill in this row beneath there. Okay, the percent of the total number of students that are girls. Okay, and again, here's the total is 14. So go ahead and do that, and then I'll fill in the third row for you. Okay, so go ahead and fill in that second row. I'm going to pause here. Okay, so let's see what you got. Okay, and we're just filling out these percents, just comparing the total number of students that are girls and then boys. And why did I not do that? Hold on a second. Okay, excuse me, let me go back. Hold on one second, I'm going to pause again and go back. Okay, so I don't know, I guess I filled this in when I did my strokes ahead of time. So yeah, so percent, if you go ahead and of course you know what we divide, we have 8 divided by 14. Okay, that's how we're going to get our percent here, and that would be 57. This is approximately 57.1%. Okay, so 57.1% of the total students in our class that are girls. And then boys, do the math there, and again I'm rounding to get these numbers. This was 42.9%. Okay, so there we go. We have okay, well, let's go ahead and work this out. Now we have the percent of the total number of students that are girls. If we go ahead and fill that in, it's 8 divided by 14. That's going to give us 57.1%. Okay, 57.1% of the students in our class are girls. And we'll go ahead and figure that out for the boys. Boys is going to be 42.9%. And again, I'm rounding, and I got that by dividing 6 divided by 14. Okay, and again, of course, percent of boys and girls in the classroom is going to be 100%, because that is everyone in our class, or all you guys, not including me, of course. Okay, all right, so now we have some more figures here. We have number of girls whose names start with a vowel. 1, no boys have names that start with a vowel. And of course our total therefore is only one person in our entire class whose names start with vowel, and that is Eva. So Eva, congratulations, being the only one. Okay, Lots of examples of names that start with vowels, but none in our class. Okay, and not even me. So if you would go ahead and let's go ahead and have you figure out the percent of girls whose names start with a vowel and percent of the boys whose names start with a vowel. And I'm going to go ahead and pause here. Okay, so we're going to figure out the percent of the girls whose names start with a vowel. Of course, that's going to be, the numbers we're going to need here are going to be 1 over 8 because we only have, again, percent of girls. Of course, of girls is going to make that our denominator. That's our whole. Okay, and we have only our lonely little Eva here with her vowel beginning name. 1 out of 8. And if we do that division, we get 12.5%. Okay, so we have 12.5% of the girls in our class have names that start with a vowel. All right. Now, we have percent of boys whose names start with a vowel. Well, that's pretty darn easy because that is just 0 out of 6, which is, of course, 0%. And I don't know why this box is here. We'll just do that. Not a very exciting prospect here. Probably could have done something different. But anyway, just to give you some ideas, working with populations, knowing, in this case, when we're doing a percent of the total number of students, we needed to use the 14 as our denominator or our whole, represent our whole, and we're talking about girls only. That number, that whole becomes 8, and it's just kind of seeing this shifting whole, okay? All right, now on the bottom here it asks us percent of total number of students that are girls whose names start with a vowel, okay? Percent of total number of students that are girls whose names start with a vowel. Now again, the only reason this is here is this idea of percent of the total number of students, okay? So the total number of students. So now, the total number of students that are girls whose names start with a vowel. Hold on 1 second. Let me pause here. Sorry, I'm just reading that wrong. But yeah, percent of the total number of students. Okay, so now we're going to use that 14 again as our denominator. Okay, and since we only have 1, that's 1 out of 14. Okay, and well, I want to have you go ahead and do that division. Come up with your answer, and then do the same, well, for the boys, of course, 0%. This is quite boring, huh? Finish this up. And come on back. Okay, there we go, 7.1% and 7.1%, and that is, of course, 1 out of 14. With no boys having a name that starts with a vowel, made that easy. Both of these answers were going to be the same. Okay, next page here. A school has 60% girls and 40% boys. Now this is going to be a little bit more interesting, and hopefully you could use your power of perseverance to figure this out. What to do with which numbers. And again, we are working with. You'll notice we're working with percents here only. Okay, because we're looking at a school has 60% girls and 40% boys. So nowhere in this problem, okay, do you see a number given, okay, a number of students, nowhere, okay. So we're going to be working with straight percentages, okay. If 20% of the girls, I'll say that again, of the girls, maybe a little bit of a hint as to which operation of math here. If 20% of the girls wear glasses and 40% of the boys wear glasses, what percent of all students wear glasses? Okay, this is one of those problems that just perplexes so many. It's like, where do I start? Well, I want you to start from what you know. Okay, use what they've given you here, and you've been given, and also what you've seen in the past. So go ahead and muddle through that one, and come on back and let's check it. Okay, so let's see where we got here. Okay, so let's work with the girls first. Okay, so we know that this school has 60% girls, and 20% of those girls wear glasses. Okay, so let's work with with those two, that 60% and that 20%. What do we do with those two percentages? Okay, so hopefully you knew what to do with those. And again, I emphasized the word of. And let's see what I did with them. Okay, so this 20% of 60%. And again, we don't have numbers, so all we can work with are these percentages. And this 60% girls is going to serve as our whole. Okay, so that 60% becomes the representation of our girls. 20% of those girls wear glasses. Therefore, we're looking for 20% of 60%. And again, like I emphasized, that of should have been a hint, a tip. It was meant to be. And that of would then assume multiplication. Okay? So what I've done, and we've been doing this quite a bit, and no surprise, I'm sure, I've just changed our 20% to be 0.2. Okay, so working with decimals, much easier, and then our 60% as 0.6. Do my very simple multiplication, and I come up with 0.12 1200ths, or also known as 12%. Okay, so what percent of all students wear glasses? We are getting there. We have our first half of it done. Okay, because now we know what 20% of 60% is. We have the girls. Our girls represent 12%. 12% of those girls is going to wear, 12% of the students in the school are going to wear glasses that are girls. Okay, so let's continue. And again, if you did this incorrectly, and you want to go ahead and work with the boys now in a similar fashion, and come on back and check your answer, please do. Highly recommend it. It's always nice to see. Again, making mistakes along the way is not a problem. It's only when we don't learn or apply what we learn from those mistakes that there's any kind of problem. Okay, so if you want to, go ahead and pause, come on back. If not, if you want to just forge through watching me do the rest, stay here. Okay, so again, now we are looking at 40% of 40%, because the school has 40% boys, and 40% of that 40% wear glasses. Okay, so now we have 40% of 40%. Again, we'll do the same as we did before. 0.4 times 0.4, because these decimals are much more friendly to work with. And then we get 0.16, which is, of course, 16%. Okay, so our answer has not yet been arrived at, because our question is, what percent of all students wear glasses? Well, if we know 12% of those glasses wearing students are girls, and 16% of those glasses wearing students are boys, then all we have to do is add them up, and we get 28%. Okay, so 28% of all students in this school wear glasses, and we got that from all of this up here. And quite remarkable what you can do if you just know how to use word clues and what we've learned so far. So if you got that, great job. If you didn't, let's see how you can do this next time. All right, so here's exercise 1, and again, this is going to this one follows on this problem here. Okay, and it asks us this: how does the percent of students who wear glasses change if the percent of girls and boys remains the same? Okay, so that is, there are still 60% girls and 40% boys. That's the same as up here, that first problem. But now it's 20% of the boys wear glasses and 40% of the girls wear glasses. That is just flipped, okay? So again, these stay the same. They're still going to be 60% girls, still going to be 40% boys, but these two aspects of that are going to flip, okay? 20% of the boys wear glasses, 40% of the girls. So, with all of that information, I would like you to go ahead and pause, give it a whirl, come on back, and we'll check. Okay, well, let's see how you did. All right, and again, 60% girls, 40%. I'm sorry, yeah, they're 60% girls. Well, we're going to work with the girls first. So now we have 60% girls, and 40% of that 60% wears glasses. So 40% of 60% equals 0.4 times 0.6, which equals 0.24, which equals 24%. So pat yourself on the back if you got that one right. Now you can see that how this number increases pretty greatly here. Okay, we had the girls before. We had 60% of the girls, but only 20% of that 60% had glasses. And you'll notice that if we compare these two numbers, that 24% is actually twice that 12%, which makes sense because we're talking about twice as many girls wearing glasses here, 40% versus 20% in our original problem. Okay? All right, so let's move on to boys. Boys, we got 40% boys and 20% of those boys wearing glasses. So we're looking at 20% of 40% equals 0.2 times 0.4, which equals 0.08, which of course, hopefully you got this, that is 8%. Okay, 8% right there. All right, and that also makes quite a bit of sense. Beforehand, we had 40% of those boys were wearing glasses. This time we had 20%, which were half as many, and 8 is half as much as 16. Okay, so that makes sense. We'll go ahead and add those up. We end up with 32%. Now, it didn't quite work out. Well, I guess it did work out because we had the girls increase by double. Girls doubled wearing glasses. Boys halved or cut in half. Okay, but 32% was the answer to that question, and it changed by looks like a net of 4%, 4% more. Okay. All right, let's move on here. We're still working with these boys and girls and their glasses. Okay. Now there's another question. How would the percent of students who wear glasses change if the percent of girls is 40% of the school and the percent of boys is 60%? So that's just flip-flopped. Okay, it was just the opposite before. And 40% of the girls wear glasses and 20% of the boys wear glasses. Okay, so we have some new numbers there. Actually, if you look, compare that to the very first question we did, actually all those percentages are the same, 40% and 60%, but now we're looking at girls going from 60 to 40, boys going from 40 to 60, and then we have 40% of the girls, 20% of the boys, which would have been same flip-flopped. Anyway, if you go back and look at that first problem, you might get a hint as to what the answer to this question is. Okay, but we are asking right here, how would it change, or how would the percent of students who wear glasses change, or would it change, or would it not change, and then tell us why. Again, do all your work here. If you don't need to do the work and you could just figure it out yourself just by looking at it, yeah, go right ahead and do that. Make your prediction. I'm going to pause here, let you do some work, let you make a prediction, and come on back. Okay, well, we're back. Let's go ahead and check this. All right. And yeah, why is the answer? Okay, so just want to show you here scenario one. I'm actually not going to, I don't think I'm doing any actual calculations, but just to go back to scenario one, we had 60% girls, 40% boys. 20% of those girls wore glasses, 40% of those boys wear glasses. So if you take a look at these numbers, you will notice something, okay? We still have 40 and 60. It's just that it's flip-flopped, okay? And we also have the same percentage distribution also with the percentage of glasses, okay? In the original scenario, we had 60% of the boys wearing, 60% of the girls wearing 20% of those 60% girls wearing glasses. In the second scenario, we now have boys as 60%, okay? And they are wearing 20%. 20% of them are wearing the glasses. So you can see the same percentage distribution, okay? 60 pairs with 20. We still have 20% of 60% here, and we still have 40% of 40% here. It's just the genders have changed. They've just flip-flopped, okay? So I saw that. I knew there was some sort of little trick to it. Not necessarily a trick. They're just trying to see if you were observant or not, okay? So we still have the same 20% of 60% and the same 40% of 40%. So we have the same percentage of students will wear glasses, okay? And that is, and again, percent. Now all these numbers could be different. We're not getting any actual number students, nominal figures, okay? We're just given percentages, okay? But it should work out, or it will work out, that same percentage of students will be wearing glasses. We haven't changed any of our percentage distribution. We just changed boys and girls, okay? So, and again, if you did all the work, you just figured it out. I'm sure you figured it out anyway, but that's fine. It's fine if you did the work to find that answer out. Okay, so now we have example 2. We're moving away from boys and girls in the school with glasses. But here we go. We're going to look at some containers, okay? A little bit different the way this is set up here. So the weight of the first of 3 containers is 12% more than the second. And the third container is 20% lighter than the second. By what percent is the first container heavier than the third container? Now, again, lots of words. To read them, to hear them, I mean, you'd still be confused, okay? But what I would like you to do is I would going to highly recommend that you draw a picture, okay, just to put it in front of you. As we've seen over and over again when we do some problems in class, it's very, very nice to have some sort of visual to look at to help you out. So I'm going to highly recommend that. I'm not going to tell you what to do, how to do it, but I'm just going to recommend a visual. So why don't you go ahead and work with that, persevere, and come on back. Okay, so let's take a look at this problem. Hopefully you set up some sort of visual, and you can see mine, very simple. Okay, I have my first container, second container, and third container. Okay, and here's how I began. I went ahead and made my comparisons. Okay, right here I'm showing that the first container is 12% heavier than the second container. Okay, the third container is 20% lighter than the second container. So hopefully you would understand, just based on what we had done in prior lessons, that you can see that both the first and the third are being compared to the second. So that makes that second container very, very important to us, okay? Because it makes it our point of reference. Okay, I'll just write these down. And as our point of reference, it becomes our 100%, okay? It is our point of reference because we're using that as the whole in this case, okay? It represents 100%. Therefore, if the first container is 12% heavier than it, it is 112% of that second container. The third container is 20% lighter than that second container, therefore it is represented by 80%. Okay, so again, we have no actual weights, we have no pounds, we have no kilograms to go by. All we have are percentages. Okay, so what that second container does is it acts as a point of reference. Okay, now we have represented the difference between container 1 and 2 with what we want to do right now, we want to go ahead and represent that difference between container 1 and 2 with the decimal equivalence of percentage. Okay, so therefore we have 112% is going to be 1.12. Take away 80%, which is 0.8. We are left with 0.32. Okay, so 0.32. And if we take that 0.32, okay, because this is the difference, okay, between 1 and 3, okay, that's the difference. And then we are going to compare that to the to number 3, okay, which is 0.8, because we're trying to find the percent difference. Okay, what percent heavier is 1 than 3? Okay, again, than 3. So therefore 3 becomes our whole, and as a result it becomes our denominator in our equation. Okay, and that equals 0.4 or 40%. Okay, 40%. So we can see by this, again, using no weights, no grams, no pounds, ounces, anything like that, just percentages, we can calculate that container 3 is 40% lighter than container 1. Okay, there we go. Container 1 is 40% heavier than 3. Okay, or vice versa. Okay, yeah, container 1 is 40% heavier than 3. Okay, now we are going to do another problem. I think the next problem is, oh yeah, and again, just, I had mentioned it before, I hadn't written it down yet, but yes, that second container in this case was our reference point, okay, or our point of reference. All right, and we'll probably see that come up again. Okay, so here we go. Yes, we are going to be able to go through this process again. This problem is going to be very similar, except that we're going to use some little doggies. Okay, we have Matthew's pet dog is 7% heavier than Harrison's pet dog, and Janice's pet dog is 20% lighter than Harrison's. Okay, and again, we can get a pretty clear idea as to which of these dogs is going to be the point of reference. Okay, and the question now is, by what percent is Matthew's dog heavier than Janice's? Okay, so again, very, very similar problem, just with names and dogs. Okay, so give you some time to muddle through that one, and hopefully you'll come back successful. Alrighty, so here we go. Coming back, hope you made a visual. I made a visual, very special visual. Here we go, let me begin. Ta-da! Okay, so that little cute little doggy there is Matthew's pet dog, and you can see he's a little chunky. Okay, he's always eating, as you can see right there. All right, we have Matthew's dog, okay, who is 70%, I mean, not 70, but 7% heavier than, bing! There is Harrison's dog, pet dog, real cute little pet dog. Okay, so we have Matthew's dog is 7% heavier than Harrison's pet dog. Okay, and then Harrison's pet dog, and we have Janice's pet dog down there. The very excitable little skinny little thing is actually 20% lighter than Harrison's. Okay, 20% lighter than Harrison's. All right, so we can see our reference point is going to be Harrison's dog, and therefore our 100%. Okay, Harrison's dog is going to act as this kind of in between. Right there is our 100%. Okay, and again, if we just do is exactly the same problem as last time. We have Matthew's dog being representing 107% because we are comparing it to Harrison's dog, our point of reference, and then we're going to have Janice's dog is going to be 80% because that's how he compares to our reference point. And the same exact thing, we have 1.07, which is 107% as using decimals, minus 0.8, which is 80% as a decimal, gives us 0.27. Okay, 0.27. Therefore, we go ahead and use, again, Janice's dog now as 80% as our whole, because we are asking that same question, what percent is Matthew's chunky dog heavier than Janice's skinny dog, okay? And if we do that, Janice's skinny dog, our 80% is our denominator, so 0.27 divided by 0.8 gives us 0.3375, which is very handily turned into a 33.75 or 33 3/4%. Okay, so Matthew's dog is 33 3/4% heavier than Janice's little skinny thing. Okay, so hopefully that went well for you using that same procedure, and you saw that it was a very much a related problem, one related to the one prior to it. I'm sure no one had as cute little doggies as I did, but yeah, hopefully I'm sure a couple of you had some drawings. Okay, and there we go. Then, boop, okay, yeah, so Matthew's dog, 33.75 or 33 3/4% heavier than Janice's dog. All right. So let's go ahead and do example 3. A little bit different. We're talking in terms of investments now, not containers or dogs. A little bit different, and let's see what you can do with it. In 1 year's time, 20% of Mrs. McElroy's investments increased by 5%. 30% of her investments decreased by 5%. And 50% of her investments increased by 3%. By what percent did the total of her investments increase? Now, this may sound like an extra difficult sounding problem that some textbook writers plan for you guys just to drive you crazy, but truth is it is very real, because what happens is as you grow older and as you it becomes more and more important to save and to have your money earn money, you have different investments, and some of those investments do a lot better than other ones. And in this case, you can see what happened to Mrs. McElroy. Miss McElroy, she may have done well in some places, because you can see she she had 20% of her investments increased. Then you had 30% of her investments decreasing by 5%. So you're going to see you can't just add all of these up simply because some are increases, some are decreases. So what I want you to do is go ahead and muddle through this one. This one's going to be a little bit different, so might take you a little bit more time to think this one through. But go ahead and give it a try. Come on back, and again, if there's any problems, we learn from our mistakes. So go ahead and give it a whirl. All right, let's go ahead and take a look at what you've done. All right, so what I first want to do is I'm going to treat these increases and decreases in a percentage fashion. So I have increased by 5%. So that I'm going to write as 1.05. Okay, and I'd love to have you in class right now where I could be talking to you. Maybe I will post a question on this one. But why did I choose 1.05? Okay. Well, I'll tell you why. Because we have an increase of 5%, and if you remember in past lessons, when we have an increase of 5%, it can't just be written as 5% or 0.05, simply because we have to account for, of course, the 100%, which is that whole. Okay. All right, so I have 1.05. What am I going to multiply it by? Well, I'm going to multiply it by, well, actually, no, I'm not doing that yet. I'm sorry. I'm going and I am looking at all these increases and decreases and how they would be represented. So you can see that increase by 5% is represented by 1.05. Now the decrease by 5%, okay, is going to be represented by 0.95, which is 95%. And then increase by 3% is 1.03. So hopefully you can see how I came up with those numbers. Okay, so I just wanted to lay those out there first, and now we need to apply those to the percentage of her investments where they belong. So 20% of her investments increased by 5%. Therefore, we have 0.2, which represents the 20% of her investments, multiplied by 1.05, because that's how much they increase, 5%. Okay, next, I take those 30% of her investments, multiply those by 0.95. Okay, so I'm going to get a number that's smaller than that 30%. Of course, simply because she lost money there. Okay, it decreased. All right, and then lastly, we had 50% of her investments increased by 3%, and that is represented there by 0.5 multiplied by 1.03. And if I do all of my math, I do my 0.2 times 1.05, I get 0.21. Okay, then I get 0.285 for my 30%, and then that last 50% gives us a factor of 0.515. Okay, now if we go ahead and add all of these up, okay, and again, these are all percentages. Okay, so these are all straight on percentages. So if we add all these up, we get 1.01, and what that translates into is 101%. Okay, so what did she start with? She started with 100%. Now this 101% sounds, wow, she increased her money by 101%, but you know what? That's not the case, okay? Because she started with 100%, so we've got to go ahead and subtract that 100% out, away from that 101%, because in the end she ended up with 101% of her money that she began with. Therefore, she only increased her investment. What percent her investments increased? Only by 1%, okay, which is a pretty poor performance, okay? I mean, sure, it's better than losing money, that's for sure, especially in a poor business or a poor stock market period, but nowadays or overall, you should definitely shoot for more than 1% growth in your money per year. Okay, but yeah, that's how that went, and hopefully that went well for you. If not, you'll have plenty of time to practice with your problem sets. Okay, and I think this might be the final exercise here. We have a concert, had 6,000 6,000 audience members in attendance on the first night and the same on the second night. Okay, so 6,000 audience members in attendance on both the first and second night. On the first night, the concert exceeded the expected attendance by 20%. So hopefully you can see where this is going. Okay, on the first night, the concert exceeded expected attendance by 20%, while the second night was below the expected attendance by 20%. Again, hopefully you can see where these are going. Above exceeding expected attendance, and then being below expected attendance, all right? So our overall answer, or the final answer we want to get is, we're trying to figure out what was the difference in percent of concert attendees and expected attendees for both nights combined. And that is a mouthful, okay? What was the difference in percent of concert attendees and expected attendees? So what we need to figure out is the concert attendees are going to be easy because we know there were 12,000 total. That's 6,000 plus 6,000. But we need to solve for this expected attendees, okay? And I'm going to have you just read that over again, get a sense of where to start, and come on back. If you want to go ahead and take it right to the end, give it a whirl, go right ahead. But if you just want to give it a start, then come on back, see where I begin. You can go ahead and then just keep pausing and going back as you get hints and tips. Okay, so why don't you go ahead? I'm going to pause. You go ahead and get started, and come on back when you're ready. Okay, so let me see. Let's get started here. All right, and I decided, and maybe you saw that this was a very good application of the Q equals P times W formula. All right, I'm going to use that for all these varying calculations. All right, so the first night, I'm going to work with the first night first. 6,000 equals, okay, so 6,000 is going to be my quantity. It's going to serve as my Q, okay? It is what we actually realize. We realize 6,000 attendees, okay? Now, that 6,000 was, it exceeded the expected attendance by 20%. So therefore, it's going to be equal to 1.2, or 120% of expectations, which is going to be our W. So that W is acting as a variable standing in for expected attendance, okay? So the 6,000, which is what we realized, is the same as or equal to 1.2 of the expected. So we go ahead and, gosh, I think you've done enough of these to just whiz through these. 6,000 divided by 1.2. So our expected, or in this case our W, the whole, which was the expected, is 5,000. So that first night, 5,000 people were expected, 6,000 showed up. Okay, so first night exceeded expectations by 1,000 people. Okay, 1,000 attendees extra, right? So let's go ahead and work on the second night. And again, if you feel you know this better now and you want to work through this second night by yourself, using what I have here or what you've written on your paper, please go ahead and pause, come on back. If not, just stick tight if you want to see how you did. All right, sticking with the same Q equals P times W formula. I have my I get my numbers. And again, I have 6,000 because that was the number of attendees that came, okay, is equal to now 0.8 W because it was below expectations by 20%. So 20%, of course, of less than 100%, of course, is 80%, which is represented as 0.8. And again, that W is standing for expected attendees. All right, and if we go ahead and do this, and again, like I said, you've done this so much, we end up with W equals 7,500. Therefore, our second night's attendance missed by 1,500, okay? Because we figured out that 6,000 represented a 20% miss. Therefore, we know that our whole or our expected had to be larger, okay? Had to be larger. And first night we went over, we knew that represented 120% of the expectations, and therefore we know that that expectation was for 5,000. So maybe it was a Friday and a Saturday, or a Saturday and a Sunday, and they expected more on the second day. But anyway, yeah, so if we add those together, I think I do that, okay? We have the expected attendance. So this final question, let me go ahead and erase this here. I made a huge mess over here. So we're going to get to answering the question because we haven't actually answered it yet. And that question goes like this: what was the difference in percent of concert attendees and expected attendees for both nights combined? So we have a little bit of work to do, okay? We know that our expected concert attendees now were 12,500, okay, because we figured out our expected for the first night, and then the second night, 5,000 plus 7,500 is 12,500. That was our expected, okay? And our realized total was 12,000, okay, because we had 6,000 on 2 nights. Both nights were 6,000, so 6,000 times 2 is 12,000, okay? And now we subtract away that 12,000 from the expected 12,500. So overall, we were 500 short, okay? We were 500 below expected attendance, okay? But we are still not at our answer, because our answer asks us what was the difference in percent of conference attendees. So we need to do a little bit of, looks like a little bit of division here. We're going to take 500, which is how much we were short, and we're going to divide that by 12,500, because that was our expected attendance, all right? And again, you can see up here, again, I'll erase my mess, all right? So you can see how this question is worded and how we plug in what we need to plug in based on how this question was worded. So what was the difference in percent of the concert attendees and expected attendees for both nights combined? Okay, so that difference between who attended and who was expected to attend. So if we go ahead and do that, we get 0.04, all right, which translates into 4% short of expectations. Okay, and that's a combined percentage there. So 4% short of expectations over the 2 nights. Okay, so 48 minutes. We're going to get done in 50 minutes here. This is really going to be a quick little lesson summary. When solving a percent problem, or percent population problem, you must first define the variable. Okay, define what we are going to use as our 100% or our reference point. This gives a reference of what the whole is. Okay, so what the whole is, and again, we're straight out percents. We never had a number other than a percent pop up in all these problems. So you can then multiply subpopulations such as girls and boys by the given category, total students wearing glasses, for example, to find the percent in the whole population. Okay, Again, I found a lot of power in using Q equals P times W, using that reference point when we had 3 different items. We knew this one, we knew this one, but we compared both to that one. Okay, so therefore we had a reference point, and that reference point always served as our 100%. Okay, and if we do that, we could just create percentages for the other items that we are comparing to it. Okay, so yeah, these population problems are things that will come up quite a bit. Hopefully you will move through and persevere through your problem set and your exit ticket. Any questions at all, I'm always available. Okay, good luck.